We look up at the night sky and see a universe that seems almost eerily uniform. No matter which direction we point our telescopes, they reveal the same. A cosmos filled with galaxies and galaxy clusters, all composed of stars and planets much like our own. But this uniformity wasn't always the way the universe worked. In fact, the universe went through a period of extreme change within the first trillionth of a second of its existence that dramatically shaped how we know it today. This period of rapid expansion, known as cosmic inflation, propelled space to immense distances at speeds faster than light. This process has had profound implications for the evolution of our universe, influencing everything from the distribution of galaxies to the very existence of life as we know it. The idea of cosmic inflation was first proposed in the early 1980s by a physicist, Alan Guth. At the time, cosmologists were struggling to explain several features of the universe that seemed at odds with conventional Big Bang theory. These include the universe's homogeneity and isotropy, the absence of a preferred starting point or direction, and the nearly perfect homogeneity of the cosmic microwave background radiation, the afterglow of the Big Bang. Guth's idea was revolutionary. He suggested that in the first fraction of a second after the Big Bang, the universe went through a period of exponential expansion, a brief but intense growth spurt that smoothed out the universe and set the stage for the large-scale structures we see today. During inflation, space expanded by a factor of at least 10 to the 26. To put this into perspective, if you were to take a raisin and blow it up to the size of the observable universe, the raisins would be separated by about 40 billion light-years. This idea solves several cosmological problems, including the horizon problem, which describes the fact that distant regions of the universe appear to be in thermal equilibrium, even though they should have been too far apart to have ever exchanged energy. Inflation also explained the observed flatness of the universe and the large-scale structure of galaxy distributions. However, inflation is not merely a theoretical construct. Its effects are detectable in the cosmic microwave background radiation, the leftover heat from the Big Bang. In 1992, NASA's Cosmic Background Explorer satellite detected tiny temperature variations in the CMB, a discovery that provided strong evidence for inflation. Subsequent missions, like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have mapped these fluctuations in greater detail, confirming predictions made by inflationary models. Despite its success, the theory of inflation leaves many questions unanswered. What caused this rapid expansion in the first place? Did this rapid expansion occur only once or multiple times? One leading hypothesis is that inflation was driven by a field known as the inflaton, which decayed into other matter after a fraction of a second, releasing huge amounts of energy that heated the universe and triggered the Big Bang. The simplest version of inflation posits that this process happened only once, giving rise to the universe we live in today. However, some physicists argue that inflation may have occurred multiple times, creating a multiverse where each inflationary bubble represents a separate universe. While these ideas remain speculative, they highlight the far-reaching implications of inflation for our understanding of the cosmos. The search for evidence of inflation is one of the most exciting frontiers in cosmology. Scientists are looking for a variety of signals, including gravitational waves, which are ripples in space-time that could have been generated during the inflationary epoch. Detecting these faint primordial waves would not only confirm the details of the inflationary process, but could also shed light on the nature of dark energy, a mysterious force that is accelerating the expansion of the universe. As we continue to probe deeper into the mysteries of our universe, cosmic inflation stands as one of the most significant developments in modern cosmology. By unraveling the secrets of this epoch, we hope to gain a deeper understanding of the fundamental nature of our reality, the origins of the large-scale structures in the cosmos, and possibly even the emergence of life itself. The story of inflation is a testament to the boundless curiosity and spirit of exploration that drives humanity's quest for knowledge. As we look to the future, the prospect of discovering new insights into this epoch promises to be one of the most thrilling chapters in the ongoing saga of cosmic discovery. The universe is vast and filled with wonders that continue to amaze scientists and stargazers alike. But have you ever wondered what was the fastest moment in the universe? What exactly happened in the first 10 to 36 seconds after the Big Bang? How did microscopic quantum fluctuations stretch to cosmic scales? And what evidence do we have for this mind-boggling event? If you're ready to blast off on a wild ride through the uncharted territory of the early universe, then fasten your seatbelts and get ready for an adventure that will redefine your understanding of time and space. Join me as we count down the fastest moment in the universe, a period so intense and brief that it defies human comprehension. But before we begin, make sure to hit that like button and subscribe for more updates on all things space. Let's dive right in. Number 10. Before the beginning. Imagine a universe devoid of galaxies, stars, or even atoms. That's what our universe was like before the Big Bang. Space and time didn't exist either. It was a realm without dimensions, a place where the laws of physics as we know them didn't apply. Then suddenly, everything changed. A quantum fluctuation, a tiny variation in the fabric of nothingness, caused space to expand rapidly in a fraction of a second, setting in motion the events that led to the formation of stars and galaxies. This moment, known as the inflationary epoch, marked the beginning of our universe, and it was the fastest moment in the history of the cosmos. 9. A sea of energy. In the first few moments after the Big Bang, the universe was a sea of energy. Fundamental particles like protons, neutrons, and electrons hadn't yet formed. Instead, the universe was a hot, dense soup of elementary particles moving at near light speed. At this point, the universe was smaller than an atom, and the temperature was over 10 trillion degrees Celsius. This extreme environment lasted for less than a second, and was the birthplace of the elements that make up our world today. 8. The strong force emerges. As the universe expanded and cooled, the strong nuclear force emerged, binding quarks together to form protons and neutrons. These particles then combined to create the nuclei of the first elements, primarily hydrogen and helium. This process of nucleosynthesis only lasted for about 3 minutes, but it was crucial for the development of the universe as we know it. Without these simple elements, stars, planets, and ultimately life could not exist. 7. The formation of atoms. After the strong force came the electromagnetic and weak forces. The universe had cooled enough for electrons to be bound to atomic nuclei, forming the first atoms of hydrogen and helium. This event marked a significant transition in the history of the universe, as the opaque plasma that had dominated the early stages gave way to a more transparent gas. The universe became less dense, and the stage was set for the emergence of larger structures, like stars and galaxies. No. 6. The cosmic microwave background. The universe was still hot and filled with light, but as it continued to expand and cool, the light began to stretch. This redshift caused the light to become less energetic, eventually becoming microwaves. Today, this ancient light, known as the cosmic microwave background, fills the universe and acts as a snapshot of the universe, as it was just 400,000 years after the Big Bang. By studying the cosmic microwave background, scientists can map the distribution of matter in the early universe and gain insights into the physical processes that shaped the cosmos. 5. The first stars appear. With the formation of the first stars, the universe entered a new era. These massive balls of hot gas dominated the landscape and provided the initial sources of light and heat that illuminated the darkness of the early cosmos. Stars played a pivotal role in the chemical evolution of the universe. Their powerful nuclear furnaces forged elements heavier than hydrogen and helium, seeding the cosmos with the building blocks of planets, asteroids, and even life itself. The appearance of the first stars marked a turning point in the history of the universe, providing the light that allowed galaxies to form and shine. Number 4. The Dark Ages. Despite the emergence of the first stars, much of the universe remained shrouded in darkness. Most of the universe's baryonic matter, the stuff that makes up stars and planets, was still in the form of an opaque plasma, preventing light from traveling long distances. This period, known as the Dark Ages, lasted until the first galaxies formed and began to illuminate the surrounding matter, gradually clearing the fog and revealing the wonders of the expanding cosmos. 3. Galaxy formation. As the universe continued to expand and cool, gravity took center stage. It pulled together vast clouds of gas and dust, which collapsed and ignited, giving birth to the first galaxies. These colossal islands of stars and planets became the building blocks of the cosmic web that stretches across the universe. Over billions of years, galaxies evolved and transformed, merging and interacting to create the awe-inspiring structures we see today. Number 2, supermassive black holes. At the heart of many galaxies lies a supermassive black hole, a region of space where gravity is so strong that not even light can escape its grasp. These enigmatic objects are the product of the relentless pull of gravity, and they play a crucial role in the evolution of galaxies. Supermassive black holes influence the motion of stars and gas within their host galaxies, shaping their structure and triggering bursts of star formation. They also play a key role in the growth of galaxies, influencing the orbits and interactions of smaller galaxies. Number 1, the expansion of the universe. From the moment of the Big Bang, the universe has been expanding, pushing galaxies and black holes apart at an accelerating rate. This expansion is driven by a mysterious force known as dark energy, which makes up nearly 3/4 of the total energy content of the universe. Dark energy is thought to be a property of space itself, and its presence has profound implications for the fate of the cosmos. As the universe continues to expand, galaxies will move away from us faster and faster, eventually disappearing from view altogether. In the blink of an eye, the universe went from nothing to everything. In less than a nanosecond, it inflated from a subatomic speck to a vast cosmos. And in just a few minutes, the simplest elements were forged. The fastest moment in the universe is a testament to the incredible power and beauty of the natural world. While we may never fully understand the complexities of the Big Bang, we can marvel at the incredible journey that brought us to where we are today. Inflationary cosmology. The inflationary epoch was a period of exponential expansion in the early universe that occurred within the first 10 to 32 seconds after the Big Bang. This theory was developed to address some of the shortcomings of the standard Big Bang model, such as the horizon problem and the flatness problem. According to this model, the universe expanded in size by a factor of at least 1026 in a fraction of a second. This expansion was driven by a hypothetical field known as the inflaton field. During inflation, the inflaton field decayed, releasing a tremendous amount of energy that reheated the universe and created the conditions for the formation of matter and radiation. One of the key features of inflation is that it predicts a nearly scale-invariant spectrum of primordial fluctuations in the inflaton field. These fluctuations would have been stretched to cosmic scales during inflation and would have acted as the seeds for the formation of galaxies and other large-scale structures. The inflationary epoch is also thought to have smoothed out the universe on large scales, explaining why the cosmic microwave background radiation is so homogeneous. Observational evidence for inflation. There is mounting evidence that supports the idea of inflation. For example, the cosmic microwave background radiation has been mapped in great detail by satellites such as COBE, WMAP, and Planck. The temperature fluctuations in the CMB align remarkably well with the predictions of inflationary models. Moreover, the large-scale structure of the universe, including the distribution of galaxies and clusters, also supports the idea of inflation. The existence of primordial gravitational waves is another piece of evidence for inflation. Gravitational waves are ripples in spacetime that can be generated by the acceleration of massive objects. Primordial gravitational waves were produced during the inflationary epoch, and their detection would provide strong evidence for this model. Currently, experiments such as LIGO and Virgo are searching for gravitational waves from the early universe. Alternative theories. While inflation is the most widely accepted explanation for the origin of the universe, there are alternative theories. One such theory is the cyclic universe model, which proposes that the universe goes through a series of big bounces, alternating between periods of expansion and contraction. However, this model faces challenges in explaining the observed features of the CMB and the large-scale structure of the universe. Another alternative theory is the steady-state model, which suggests that the universe has no beginning or end, and that it has always existed in its current state. However, this model conflicts with the observed expansion of the universe and the abundance of light elements. Conclusion. The inflationary epoch is a fascinating and highly debated topic in cosmology. The theory of inflation has been remarkably successful in explaining many of the features of the early universe. However, there are still open questions and alternative theories that need to be considered. Further observations and theoretical developments will continue to shed light on the origin and evolution of our universe. The origin of life, the birth of stars, the grand design of the cosmic web, they all find their roots in a period known as inflation, a mere fraction of a second in the universe's history. Inflation, with its radical idea of a rapidly expanding universe, forever altered our understanding of cosmology. And one of its most intriguing legacies is the concept of iconic objects. These aren't relics from some ancient civilization, but rather the imprints of quantum fluctuations during the inflationary epoch. They're the building blocks of the universe, stretched across cosmic distances and serving as the foundation for everything we see around us. But what exactly are these iconic objects? How do they manifest in our universe? How do they help us understand the fundamental workings of our reality? This is our channel, and today we're embarking on a journey to uncover the secrets of iconic objects, the quantum seeds that shaped our universe. Before we dive into the world of iconic objects, let's first understand the concept of inflation itself. Imagine our universe as a vast ocean. Now picture a tiny ripple spreading across its surface. That ripple carries energy, just as waves crashing on a beach carry the energy of the wind. Similarly, the universe didn't just start out as a hot, dense singularity. It underwent a period of exponential expansion, a cosmic inflation driven by a field called the inflaton field. But here's the twist. This field wasn't uniform. It had quantum fluctuations, tiny ripples of energy spread throughout. Think of these fluctuations like the random motion of air molecules, constantly shifting and changing. These quantum fluctuations in the inflaton field are the origin of iconic objects. Now let us take a deep dive into what these iconic objects are and how they evolved into the structures we see in the cosmos. As the universe began to expand, these quantum ripples of the inflaton field stretched across the vast canvas of space. What went from being microscopic became cosmic. This stretching didn't change the overall nature of the fluctuations, but it amplified them. These once tiny quantum variations grew into significant density fluctuations in space. So how did these density fluctuations shape the universe? Picture a vast cosmic ocean. Where the inflaton field was more dense, there was a stronger pull. Think of it like a deeper part of the ocean. The matter in those regions was drawn towards those dense areas, creating a kind of gravitational well. Over time, as the universe continued to expand and cool, this drew together normal matter and dark matter to form the first seeds of galaxies and clusters of galaxies. Meanwhile, where the inflaton field was less dense, matter had fewer places to gather, resulting in vast empty regions in space. Thus, this process led to a universe dotted with massive structures separated by huge voids. This pattern is strikingly similar to the large-scale structure of the universe we observe today, a cosmic web of filaments and clusters of galaxies with immense voids in between. This brings us to the next point. Do we have evidence for iconic objects in the universe today? The answer is yes. We have indirect evidence from the cosmic microwave background, the leftover radiation from the Big Bang. The cosmic microwave background, it's often shortened to the CMB, is the oldest light we can see in the universe. When the universe was just 380,000 years old, the cosmos was hot and filled with a sea of particles, photons. The particles of light were constantly interacting with these particles. This interaction kept photons from traveling freely. But as the universe expanded and cooled, these particles combined to form neutral atoms, mostly hydrogen. This crucial event released a surge of free photons, which have been zooming through space ever since, giving us a direct window into the past. Today, satellites like COBE, WMAP, and Planck have mapped this ancient light with incredible detail, and what they found is a universe full of tiny temperature variations. These are the imprints of the iconic objects. Some regions of the CMB are slightly hotter, indicating areas where the early universe was slightly more dense. These dense regions became the seeds for the galaxies and clusters of galaxies we see today. Other regions of the CMB are cooler, indicating less dense areas. These regions formed vast voids, enormous expanses, almost devoid of matter. Together, the hot and cold regions create a map of the early universe that closely matches the structure of the universe as we know it today. What's even more remarkable is that the patterns in the CMB match the predictions of inflation almost perfectly. This agreement provides strong support for the theory of inflation and serves as tangible evidence for the existence of iconic objects. Let's now talk about another fascinating aspect of iconic objects: their role in seeding the supermassive black holes at the centers of galaxies. The largest black holes in the universe, the supermassive ones, also seem to have their origins in these iconic objects. During inflation, quantum fluctuations in the inflaton field would have created tiny variations in the distribution of dark matter. These variations provided the initial seeds for the formation of galaxies. But within these nascent galaxies, there would have been small variations in the distribution of matter. The denser regions within these regions of dark matter became the seeds for the first stars, and these in turn gave rise to the supermassive black holes we see today. Another exciting development in this field is the potential detection of primordial gravitational waves. These waves are ripples in the fabric of space-time itself. Detected, they provide direct evidence of inflation and give us a unique window into the earliest moments of the universe. Several experiments are searching for these waves, including BICEP 2, located at the Amundsen-Scott South Pole Station. While some initial results were met with excitement, further analysis revealed that the signal might have been caused by galactic dust. However, upcoming experiments, such as the Simons Observatory and the Laser Interferometer Space Antenna, LISA, are poised to make groundbreaking discoveries in this area. The detection of primordial gravitational waves will not only confirm the predictions of inflation, but also open up new avenues in our understanding of the universe. So how do scientists study these iconic objects? Cosmologists use computer simulations to model the evolution of the universe from the initial quantum fluctuations of the inflaton field. These simulations involve complex mathematics and the use of supercomputers to solve the equations that govern the behavior of matter and energy in the universe. By running these simulations, scientists can track how matter evolved under the influence of gravity, eventually forming the large-scale structure of the universe. One such simulation is the Millennium Simulation. It followed the evolution of 10 billion particles over a period of 6.4 billion years. This simulation vividly illustrates how iconic objects gave rise to the rich tapestry of our universe. The simulation starts with a universe filled with randomly distributed particles representing the quantum fluctuations of the inflaton field. Over time, these particles collapse under the force of gravity, forming smaller and larger structures. The simulation accurately depicts the hierarchical formation of cosmic structures. Initially, small clouds of gas collapse to form stars. As time progresses, these stars congregate into galaxies. Galaxies merge to form clusters, which in turn come together to create the large-scale filaments and sheets of the cosmic web. The simulation shows how the universe evolved from a state of simplicity to the complex web of galaxies and clusters we observe today. It's a testament to the power of computer simulations in unraveling the mysteries of the universe. The study of iconic objects is an active area of research in cosmology. Scientists are working on refining computer simulations to better understand the details of structure formation. Additionally, experiments like the Square Kilometre Array, SKA, provide high-resolution maps of the cosmic microwave background, allowing scientists to probe the imprints of iconic objects in greater detail. As we conclude our exploration of iconic objects, let's reflect on their profound implications. These quantum seeds of inflation have shaped the universe on the largest scales, orchestrating the formation of galaxies, clusters, and the cosmic web. They're a reminder of the interconnectedness of the very small and the unimaginably vast. The study of iconic objects has revolutionized our understanding of the universe, demonstrating the elegance and predictive power of the inflationary model. It's a testament to the human spirit of exploration and our relentless pursuit of knowledge. As we continue to explore the cosmos, we're not just discovering distant galaxies and clusters, we're re-uncovering the very origins of cosmic structure and the seeds that gave rise to our universe as we know it. When we peer into the depths of space, we're actually looking back in time. Light takes time to travel, and the farther away an object is, the farther back in time we're seeing it. But what we're really seeing is the imprint of the early universe. The cosmic microwave background radiation is a snapshot of the universe. When it was just 400,000 years old, studying this ancient light, scientists have uncovered remarkable insights into the universe's evolution. And now they're on the trail of two of the most intriguing concepts in modern cosmology: cosmic inflation and the eternal inflation multiverse. Cosmic inflation, a brief but explosive chapter of the Big Bang Theory, describes the evolution of the universe from an extremely hot, dense state. However, this initial singularity poses a problem. For the theory to work, the universe must be perfectly smooth and featureless at very small scales. But astronomers see no evidence of this. Instead, they observe a nearly uniform cosmic microwave background with tiny variations. These variations can be explained by quantum fluctuations. But as the universe expanded, these fluctuations should have been stretched and smoothed out. How did they get back in? The answer came with the idea of cosmic inflation. In the first fraction of a second after the Big Bang, the universe went through a period of exponential expansion, much faster than the speed of light. This rapid inflation smoothed out any initial irregularities and stretched quantum fluctuations to observable scales, creating the seeds for galaxy formation. It also solves several long-standing problems in cosmology. For example, it explains why the universe is so homogeneous on large scales. If it wasn't initially smooth, inflation could have smoothed it out. Furthermore, it predicts a nearly flat universe, which observations confirm. The inflated field, the driving force behind expansion, what caused this explosive expansion? The answer is an invisible energy field, called the inflated field. Initially, the inflated field permeates the entire universe with a high energy density. As it rapidly decays, its energy is converted into particles and light, populating the universe and ending inflation. But not all models require the inflated field to decay. In some scenarios, it simply drops to a lower energy state, causing the accelerated expansion we observe today. This has led to the idea of quintessence, a hypothetical particle that drives dark energy. Eternal inflation, a never-ending story. One of the most exciting but also controversial aspects of inflation theory is eternal inflation. Standard inflation proposes that the universe underwent a brief period of exponential growth followed by a slowdown due to the decay of the inflated field. But eternal inflation suggests that inflation never ends. Somewhere in the vast expanse of the cosmos, the inflated field continues to expand exponentially, creating new regions of space where the universe is still inflating. But how can we ever detect something that isn't expanding into our observable universe? The answer lies in the collisions between inflating bubbles. Imagine the universe as a patchwork quilt made up of numerous patches, each corresponding to a bubble of inflating spacetime. When two patches collide, the imprint of their interaction could be detected in the cosmic microwave background. The key to finding these collisions is looking for anomalies in the temperature and polarization of the CMB. However, it's important to note that detecting such collisions would only prove the occurrence of inflation. It wouldn't necessarily verify the eternal inflation scenario. In fact, many physicists believe that eternal inflation is mathematically possible, but physically meaningless, because we can never observe the parts of the universe outside our observable horizon. However, this doesn't diminish the significance of studying eternal inflation. It helps us better understand the mechanisms driving inflation and provides insights into the nature of the inflated field. The multiverse and the anthropic principle, eternal inflation, naturally leads to the idea of a multiverse. If new bubble universes are constantly being created, then there are countless universes beyond our observable one. Moreover, these universes may have different physical properties. Different regions of the inflated field could result in different values for physical constants. Some universes might have more dimensions or different types of particles. In fact, string theory supports this idea. It suggests that the properties of fundamental particles and the strength of forces depend on the size and shape of extraspatial dimensions. These dimensions are thought to be compactified or curled up, and the exact way they are compactified determines the physical properties of a universe. This means that, in a multiverse, there would be a vast array of universes with different physical laws and constants. Now you might be wondering, why do we live in a universe that is suitable for life? Why are the physical constants finely tuned for life as we know it? There are many possible explanations for this puzzle. One popular idea is the anthropic principle, which essentially says that we are here because the conditions are right for us to be here. But this idea is highly speculative and lacks a strong scientific basis. Other physicists argue that the apparent fine-tuning of the universe is an indication that there are other universes with different properties, and we just happen to live in the one that is suitable for life. This idea is appealing because it sidesteps the anthropic principle, but it also leads to the question, if there are other universes, why haven't we observed any evidence for them? The multiverse detection efforts, while directly observing other universes, is beyond our current technological capabilities. Scientists are searching for indirect evidence, anomalies in the cosmic microwave background or large-scale surveys of galaxy distributions. This may hold clues about the nature of eternal inflation in the multiverse. The detection of a cold spot in the CMB, though not statistically significant, has been proposed as evidence of a collision with another bubble universe. Similarly, unusual features in the distribution of galaxies could point to the influence of nearby inflating regions. Future missions such as Planck and WMAP will map the universe in greater detail, searching for these subtle hints of other worlds. Advanced computer simulations are also helping to unravel the complexities of eternal inflation. By modeling the behavior of the inflated field, scientists can simulate the formation of bubble universes and their subsequent collisions. These simulations can then be compared with observations to refine models and search for signatures of eternal inflation. The philosophical puzzle, eternal inflation, challenges not only our understanding of physics, but also our philosophical assumptions about reality. If an infinite ensemble of universes exists, each with its own physical laws and constants, then the concept of uniqueness loses meaning. Every possible outcome occurs somewhere, raising questions about determinism and the role of chance. It also blurs the boundary between science and speculation, forcing us to confront the limitations of human knowledge. Fine-tuning, in the anthropic principle, the apparent fine-tuning of the universe, with physical constants that seem perfectly suited for life, remains a profound mystery. Eternal inflation offers one possible explanation. If there are countless universes with a wide range of properties, then it is not surprising that we find ourselves in one that is hospitable to life. This interpretation, however, delves into the realm of philosophy, touching upon the anthropic principle and the limits of scientific inquiry. What lies ahead? Despite the many challenges and controversies, eternal inflation and the multiverse remain among the most compelling and imaginative ideas in modern cosmology. The quest to understand the true nature of reality is a journey into the unknown, driven by human curiosity and the desire to comprehend the vastness and complexity of the universe. As technology advances and our understanding of physics deepens, we may uncover new insights into the origins and evolution of our universe. Who knows? We might even find traces of other bubble universes, confirming the existence of a grand multiverse. In the 1930s, physicist Pascal Jordan remarked, "God created the world in 40 days. And then he looked around and said, 'This is good, but it could be better.'" So he introduced quantum mechanics. And while it might be tempting to roll our eyes at such anthropomorphic speculation, Jordan's quip contains a kernel of insight into what makes our universe so special. Our existence hinges on the fact that the laws of nature are finely tuned to allow for the formation of planets and stars, chemistry and life. But why? Why are the laws of nature so finely tuned for life? What if they weren't? What if fundamental constants took on different values? Would the universe still exist? Or would we find ourselves hurtling through an alien landscape so hostile that not even a single molecule could persist? To answer this question, we need to look back to the very beginning, to a time before atoms, before light, before space and time were even defined, a period known as the inflationary epoch. It occurred a fraction of a second after the Big Bang. During this brief instant, space expanded faster than the speed of light, stretching and smoothing out the universe as it grew. It was an explosive era that produced the blueprint for everything we see around us today. Yet for all its importance, inflation lasted less than a nanosecond, 10 to the negative 33rd power seconds, so brief that any trace of it has since vanished. All evidence of this epoch now lies encoded in the structure of the universe itself. One of the most compelling pieces of evidence comes from observations of the cosmic microwave background, or CMB. This faint glow permeates the universe and represents the remnants of light from the Big Bang. The CMB reveals that the universe in its infancy was remarkably uniform, a feature that has puzzled scientists for decades. How could every part of the universe be so similar when we know that parts of the universe are so incredibly distant that they should not be able to interact? Albert Einstein's theory of general relativity says that nothing can travel faster than the speed of light. Thus, in the first moments after the Big Bang, when the universe was much smaller, all regions were causally connected. However, the universe has expanded dramatically since then. Parts of the universe that are now billions of light years apart must have been separated from each other long before light had a chance to reach them. Yet the temperature of the CMB is almost the same across the entire sky. This uniformity implies that the universe was highly homogeneous and isotropy long before the epoch of nucleosynthesis. When protons and neutrons combine to form atomic nuclei, how did this happen? Enter cosmic inflation, a period of exponential expansion in the first moments of the universe. During this time, the universe increased in size by a factor of 2.6 trillion in less than 1/10,000,000,000th of a second. The inflationary epoch leveled out any initial irregularities, smoothing the fabric of space-time and giving rise to the universe as we know it. Now, you might be wondering what caused this inflation, and fair enough, we don't know yet. To account for this puzzling aspect, physicists have introduced a hypothetical field known as the inflaton field. This field supposedly pervaded the early universe and decayed into other particles after the inflationary epoch ended. But the mechanism driving this decay remains unknown. Scientists do know, however, that the inflaton field must have been extremely uniform for inflation to occur. This uniformity allowed the quantum fluctuations of the field to propagate evenly throughout the universe, ensuring a homogeneous distribution of matter after the inflationary epoch ended. The decay of the inflaton field produced the particles that eventually evolved into galaxies, stars, and planets. These particles inherited the homogeneity of the inflaton field, explaining the uniformity of the CMB. But wait, there's more. The inflationary field did not just smooth out the universe. It also stretched the quantum fluctuations of space-time to enormous scales. And these stretched fluctuations are thought to be the seeds from which galaxies formed. Thanks to inflation, our universe isn't just uniform, it's almost perfectly flat. In technical terms, the overall curvature of space is extremely close to zero. Without inflation, the universe would have been subject to strong positive or negative curvature, leading to significant variations in density and possibly preventing the formation of large-scale structures like galaxies. Positive curvature would cause parallel lines to converge, while negative curvature would cause them to diverge. But inflation smoothed out these effects, leaving us with a universe that is remarkably flat. This flatness has profound implications for Earth. It means that orbits like that of our solar system are stable over billions of years. If the universe had a positive or negative curvature, orbits could become unstable, disrupting planetary systems and potentially destroying Earth itself. Another remarkable feature of our universe is the near equality of matter and antimatter. When matter and antimatter meet, they annihilate each other, releasing tremendous energy. At the end of the inflationary epoch, the universe was filled with high-energy particles, including pairs of matter-antimatter particles. If the amount of matter and antimatter were exactly equal, they would have completely annihilated each other, leaving behind a universe devoid of matter and light. However, observations of the universe tell us that there is slightly more matter than antimatter. This imbalance, although tiny, is crucial. It means that some matter survived the annihilation, providing the building blocks for stars, galaxies, and ultimately life. Although the exact origin of this asymmetry remains uncertain, conditions established during inflation may have played a vital role. The extreme conditions of the inflationary epoch could have influenced particle interactions, potentially leading to a slight excess of matter over antimatter. So inflation touches upon another remarkable feature of our universe, the existence of dark matter. Dark matter is an invisible substance that makes up a significant portion of the mass in the universe. Its presence is inferred from its gravitational effects on galaxies and clusters of galaxies. Scientists believe that dark matter played a critical role in the formation of large-scale structures in the universe. The idea that dark matter was important in the early universe goes back to the 1980s. It was noticed that the abundance of light elements such as hydrogen and helium in the universe did not match the predictions of the Big Bang model. This discrepancy could be resolved if there existed a type of non-baryonic matter, a form of matter that did not consist of protons and neutrons. This idea was further bolstered when computer simulations of galaxy formation showed that the observed distribution of galaxies could be reproduced if a non-luminous form of matter dominated the mass of the universe. This mysterious substance came to be known as dark matter, and according to inflationary models, dark matter would have been produced during the decay of the inflaton field at the end of the inflationary epoch. Inflationary theory naturally incorporates the idea that the inflaton field decays into pairs of normal matter and dark matter particles. This process would ensure that dark matter was evenly distributed throughout the universe. Today, dark matter is thought to make up roughly 80% of the matter in the universe and plays a key role in the formation of galaxies and larger structures. The inclusion of dark matter in inflationary models elegantly resolves the issues with the Big Bang nucleosynthesis and the large-scale structure of the universe. It provides a framework that can explain how galaxies form and evolve over time. And let's not forget about the very existence of the Milky Way itself. The Milky Way is home to hundreds of billions of stars, including our Sun. These stars didn't just pop into existence. They evolved from vast clouds of gas and dust that collapsed under their own gravity. Inflation seeded these clouds with tiny density variations. Over millions of years, these variations grew, forming the spiral arms and the disc-shaped halo of the Milky Way. Our solar system sits within the Milky Way, and Earth, with its unique conditions, is a part of this cosmic marvel. The very existence of our planetary home is a testament to the success of inflation in creating a universe hospitable to life. As scientists continue to probe the mysteries of the universe, cosmic inflation stands as a cornerstone of modern cosmology. The inflationary epoch, though fleeting, had repercussions that echo to this day. It shaped the large-scale structure of the universe. It influenced the formation of galaxies, stars, and planets. It set the stage for the conditions necessary for life to flourish on Earth. By understanding inflation, we come to appreciate the delicate balance that has allowed life to emerge and thrive in this corner of the cosmos. The story of Earth is inextricably linked to the fate of the universe, and the tale of the universe begins with inflation. The human gaze has always sought to see beyond what's immediately visible, to peer into the heart of distant stars or the depths of the very cosmos. This innate curiosity has driven us to develop some of the most ingenious instruments ever conceived. But sometimes the most audacious journeys are inward, delving into the history of our universe itself. Such is the case with BicePet 2, a groundbreaking experiment that set out to see the birth of the cosmos. In the late 20th century, cosmologists were faced with a puzzle. The Big Bang Theory elegantly explained many aspects of our universe, but it could not account for the universe's large-scale structure, or the nearly perfect uniformity of the cosmic microwave background. Enter Alan Guth's theory of cosmic inflation, a brief period of exponential expansion in the universe's first moments. This groundbreaking idea proposed that quantum fluctuations stretch to vast scales during this rapid inflation, leaving an imprint on the fabric of space-time. While the Big Bang Theory described the evolution of the universe after this inflationary period, Guth's theory addressed the conditions that prevailed in the universe's first fleeting moments, offering a solution to the puzzles that plagued the Big Bang model. By the mid-1990s, the idea of cosmic inflation was generally accepted among cosmologists, but direct observation remained elusive. Enter NASA's Boomerang and the Wilkinson Microwave Anisotropy Probe, WMAP, which detected tiny temperature fluctuations in the cosmic microwave background, precisely the type of information Guth had predicted. This discovery lent powerful support to his theory. Then in 2009, the European Space Agency's Planck satellite took to the skies, equipped with a 1.5-meter gold-plated telescope designed to peer deep into the infrared. Its mission: produced the most accurate map yet of the cosmic microwave background. What made Planck's mission particularly intriguing was its potential to detect the elusive B-mode polarization pattern in the CMB. This polarization pattern is thought to have been caused by the stretching of space-time during the inflationary epoch. If detected, it would offer undeniable evidence for Guth's theory. After meticulously scanning the sky, Planck revealed that the temperature fluctuations in the CMB were remarkably homogeneous, providing further confirmation of inflation. However, the highly anticipated B-mode polarization data was inconclusive. Despite this setback, Planck's legacy extends beyond its immediate findings. Its precise measurements of the cosmic microwave background have set the stage for future experiments like BICEP, whose ambitious goal is to detect the B-mode polarization signal with unmatched sensitivity. Located at the Amundsen-Scott South Pole Station, a research facility operated by the University of Wisconsin-Madison in Antarctica. These telescopes are housed within two 1-meter diameter cryogenic vessels, cooled to a frigid 250 millikelvin, roughly 400 times colder than outer space. Inside each vessel, a superconducting single-pixel device called a transition edge sensor, or TASE, acts as the instrument's detector. A thin metal strip is positioned in front of the sensor, and two horns focus incoming radiation onto the strip. One horn is oriented vertically, while the other is oriented horizontally. This setup enables the detection of both E-mode and B-mode polarized signals. The BIP-2 telescopes are tuned to detect a specific range of frequencies, approximately 100 GHz, where the cosmic microwave background signal is strongest. To achieve the necessary sensitivity, every component must be meticulously shielded from external sources of noise. Electrical and mechanical vibrations are isolated using pneumatic systems, and acoustic and magnetic interference is minimized through careful design and material choices. Furthermore, the entire system is enclosed within a vacuum chamber to prevent heat and humidity from degrading performance. In essence, BIP-2 is an exceptionally sensitive experiment designed to detect faint signals originating from the early universe. The quest to observe the universe's birth has led to some truly extraordinary places, both physically and metaphorically. Consider the journey to the South Pole, a site chosen for its strategic advantage in observing the cosmos. Here, beneath layers of ice, a team of scientists braves extreme cold and isolation to operate one of the world's most advanced experiments. This dedication underscores the lengths to which humanity will go to probe the origins of our existence. But there's more to the story. Behind the scenes, engineers and technicians work tirelessly to maintain and upgrade equipment, ensuring that it can withstand the harshest conditions. They are the unsung heroes who make groundbreaking discoveries possible. Meanwhile, data analysts sift through terabytes of information, searching for the subtle signals that hold clues to the universe's infancy. Their work, often unseen, is vital in extracting meaningful insights from the raw data collected by the telescopes. And let's not forget the theorists who interpret the results. They develop models and simulations, weaving together the complex tapestry of physics that helps us understand the implications of what we find. BICEP-2's observations have profound implications that extend beyond the scientific community. They touch upon fundamental questions about our place in the universe and the nature of reality itself. The detection of the B-mode polarization signal would provide direct evidence for cosmic inflation, revolutionizing our understanding of the universe's beginnings. This quest for knowledge, for understanding, is a testament to human curiosity and our relentless pursuit of answers. The stakes are high, the challenges are immense, but the potential rewards are beyond measure. Every measurement, every analysis brings us closer to unraveling the secrets of the universe and our place within it. The story of BIP-2 is one of exploration, discovery, and the relentless pursuit of knowledge. It's a story that reflects our deepest human instincts, our innate curiosity about the world around us. From the intrepid scientists and engineers who brave the elements to the data, analysts and theorists who piece together the puzzle of the universe, we are all part of this incredible journey. So keep looking up, keep asking questions, and keep exploring. Who knows what wonders we might uncover next? The allure of the unknown has always beckoned humanity forward, driving exploration and discovery. Today, we stand on the threshold of a new frontier in our quest to understand the birth of our universe. As of the latest updates, the BICEP collaboration has yet to confirm the detection of primordial gravitational waves. The data collected by BIP-2 in 2015 hinted at a possible signal, but subsequent analysis revealed that it could be attributed to dust in our galaxy, the Milky Way. However, the quest is far from over. Experiments like BIRD-3, the Simons Observatory, and the LightBird mission continue to refine their observations. The scientific community eagerly awaits their findings, hoping to finally confirm or refute the presence of primordial gravitational waves. The search for the fingerprints of inflation is more than a scientific endeavor. It's a testament to human curiosity and our relentless pursuit of knowledge. Whether or not we find the signals we seek, the journey itself expands our understanding of the universe and our place within it. Every measurement, every analysis brings us closer to unraveling the mysteries of the cosmos. Imagine a world without Google, a world where finding information meant poring over countless books and documents. Now imagine explaining complex topics like quantum mechanics or astrophysics without the aid of visuals. It would be a Herculean task indeed. That's where Brilliant comes in, an online learning platform offering thousands of interactive lessons in math, science, and engineering. Brilliant uses a unique approach to learning, focusing on problem solving and critical thinking through interactive modules. You won't find lengthy lectures or confusing textbooks here. Instead, Brilliant offers bite-sized lessons that fit seamlessly into your day, whether you're a student, a professional, or simply someone with an insatiable curiosity. Learning on Brilliant is an enjoyable and rewarding experience. With thousands of lessons covering everything from foundational and advanced mathematics to AI neural networks and quantum computing, there's something for everyone. In the tapestry of cosmic discovery, we have come upon a profound mystery, a fleeting instant in the universe's dawn, a fraction of a second in the first trillionth of a second after the Big Bang. It is a tale of unimaginable energy, of space expanding faster than the speed of light. This is the story of inflation, a mere heartbeat in the universe's history, yet pivotal in shaping everything we know. As we peer into the abyss of space and time, we seek to unravel the secrets of this inflationary epoch. How did the universe, with all its vastness and complexity, arise from such a humble beginning? Was there a force that set the stage for the cosmic drama that was to unfold? The answer to these questions may lie hidden in the faint whispers of radiation that have traveled across the cosmos for billions of years. Whispers that speak of an era when the very fabric of space-time was transformed. Inflation, a concept born in the minds of brilliant scientists, is more than a theory. It is a beacon guiding us through the darkness of the unknown. It tells us that our universe, with its galaxies and stars and planets, its atoms and molecules and living beings, emerged from a quantum fluctuation, a random variation in a sea of energy. The inflationary epoch is thought to have lasted for a period so brief that it defies our human comprehension. From 10 to the negative 36 seconds to 10 to the negative 33 seconds. In that infinitesimal span, space expanded by a factor of 1, followed by 26 zeros. To put this in perspective, it est as if you were to take a raisin and instantly transport it to a location 900 times farther away. That's the scale of inflation. But why should we believe in inflation? What evidence do we have for this extraordinary claim? Let's delve into the clues that point towards this monumental event. The universe we inhabit is filled with a faint glow known as the cosmic microwave background radiation. It is a relic from the early days of the universe, a snapshot of the cosmos as it was just 400,000 years after the Big Bang, when the universe was still a hot, dense soup of elementary particles. But as the universe expanded and cooled, atoms formed and light began to stream freely, illuminating the cosmos with a faint glow that has endured for billions of years. This cosmic microwave background is not just a beautiful curiosity. It is a treasure trove of information about the early universe. By analyzing its subtle variations, scientists have pieced together a detailed picture of the universe's evolution from its earliest moments. And here's where inflation leaves its indelible mark, according to the theory. The rapid expansion of the universe during inflation would have generated a tiny amount of gravitational waves. These are ripples in the fabric of space-time itself. Gravitational waves are disturbances in the curvature of space-time that propagate at the speed of light. They were first predicted by Albert Einstein in 1915 as a consequence of his general theory of relativity. Just like ripples spreading across a pond after a stone is tossed in, gravitational waves carry energy away from their source. But unlike ripples on a pond, these cosmic ripples can stretch and distort the very essence of space-time. If we could see these gravitational waves, they would appear as a sort of B-mode pattern in the cosmic microwave background. This B-mode signal is incredibly hard to detect, but several experiments are searching for it. One of the most ambitious is the BICEP collaboration. After years of analysis, They have claimed to have found evidence of inflation in the B-mode polarization of the cosmic microwave background. This is a remarkable development, but it has also been met with some skepticism. Other teams are now scrutinizing the data to confirm these findings. If true, this discovery would not only validate the theory of inflation, but also open up new vistas in our understanding of the universe. It would provide a glimpse into the quantum fluctuations that shaped the cosmos and potentially offer insights into the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Simulations based on inflationary models have shown that the gravitational waves produced during this epoch would leave a distinct imprint on the cosmic microwave background. And while detecting these signals is challenging, it is not impossible. Enter the LIGHTBIRD mission, a Japanese space project planned for the late 2030s. LIGHTBIRD, short for Light Scout, is designed to do just that. It will be equipped with a highly sensitive telescope that will scan the entire sky to map the polarization of the cosmic microwave background. With its advanced technology, LIGHTBIRD will have the capability to detect the faintest of signals, offering an unprecedented view of the universe's infancy. This mission holds the potential to revolutionize our understanding of the universe. If successful, it could provide the first direct evidence of inflation, validating decades of theoretical work and opening up new frontiers in cosmology. But what if inflation isn't eternal? What if it ended right after that initial burst of rapid expansion? This seems likely because the inflated field must decay rapidly and completely. Otherwise, there wouldn't be enough energy for the formation of matter. Therefore, we expect the entire process to be over in a trillionth of a second. Interestingly, if it doesn't happen quickly, we will see signs of it today. The decayed products of the inflated field would accumulate and eventually become noticeable. However, there is another intriguing possibility. What if inflation continues in some places while ending in others? This leads us to the concept of eternal inflation. In this scenario, our universe is just one bubble in a vast multiverse, a realm where countless other universes exist. Each bubble is a separate region where inflation continues, creating new universes with their own physical laws and constants. In this eternal inflationary multiverse, we would not be able to see the other universes, because they are causally disconnected from each other. We would only be able to see inside our own bubble. So in a sense, this eternal inflation is a bit like the heat death of the universe. Even though there are other universes out there with lots of energy, we can't see them. Eternal inflation has been criticized for being a scientific dead end, a theory that cannot be tested. But this is not entirely accurate. There are ways to test this scenario, albeit indirectly. For example, if eternal inflation is true, then we would expect to see the occasional collision of a new bubble with ours. These collisions would produce gravitational waves that could potentially be detected by experiments like LIGO or Virgo. Additionally, the decay products of the inflated field and the colliding bubble could leave imprints on the cosmic microwave background. While these scenarios may seem far-fetched, they are not beyond the realm of possibility. And as our observational capabilities improve, we may find indirect evidence supporting or refuting eternal inflation. The significance of inflation extends beyond the realm of scientific inquiry. It touches upon profound philosophical questions about our place in the universe. The realization that our existence is the result of a quantum fluctuation during inflation underscores the fragility of life. It reminds us that the conditions that led to our being are so delicately balanced that even the slightest change could have resulted in a universe incapable of supporting life as we know it. Yet here we are, marveling at the very forces that brought us into existence. Inflation is a humbling experience, pushes the boundaries of our knowledge, and challenges our understanding of the universe, compels us to confront the mysteries of quantum mechanics and the nature of reality itself. As we continue to explore the implications of inflation, we may find answers that reshape our perception of the cosmos and our place within it. It is a journey that promises not only to expand our scientific understanding, but also to deepen our appreciation for the wonders of the natural world. The inflationary epoch, a mere heartbeat in the universe's history, has left an indelible mark on the cosmos. It is a testament to the power of quantum fluctuations and the relentless drive for simplicity in the laws of nature. But as we look back at this momentous event, we must also look forward. The future of cosmological research lies in new missions and bold ideas. that will continue to unlock the secrets of the early universe. From the Simons Observatory to the Lightbird satellite, each project brings us closer to the moment when we might finally answer some of the most fundamental questions about our existence. In the end, the story of inflation is not just about the past. It is about us, our place in the grand tapestry of the cosmos, and our insatiable curiosity about the universe and its origins. Every discovery we make about inflation is a step towards understanding ourselves better. It is a reminder that we are not merely observers of the universe, but active participants in its evolution. We are the storytellers of the cosmos, and our story is forever intertwined with the fate of inflation.